So as we'll see, and I'll have a demonstration for you involving the Van de Graaff and this little glass tube. Do you guys remember these from chemistry last year? No, chemistry wasn't last year. Do you guys remember these? Do you look at these through like spectroscopes to split the... What's that? Oh, that's right. That's right. Well, we should probably talk about it because that's how electrons emit photons of light. That's how photons of light are emitted, by accelerated electrons. And it's a good way to see it. But anyway, so it is not the electric potential. Yesterday we defined the electric potential. We saw that it was the negative integral from R to infinity of the electric field dotted with dr. So this is a vector field equation that deals with the electric field itself. Remember, this came from relating the electrical potential energy to the work done. I'm not going to go through that whole thing again. To the work done by the applied force, but then we don't want to use the applied force because that would not be a more generalized force. The electric force is generalized. And then I divided both sides by Q. And then I get that, force per unit charge is electric field. Electric potential energy per unit charge is voltage. But voltage isn't important. If every point in the universe was at the same voltage, guess what would never move?
Everything.
Everything with
mass.
Electric charge.
Electric charge.
Yeah, that's probably not a great question. But yeah, if every point in the universe was at the same voltage, the same electric potential, nothing would move. Nothing would move. No charges would flow. No electricity would be had. None of that. Okay. So what really is important is not an electric potential, but an electric potential difference. There you go.
Jeez, guys, come on.
Now we got this from potential energy. We want to kind of leave potential energy behind, and then go to, okay, yeah, I need a potential difference. So it's not V that's super important as far as making stuff happen. It is delta V. And make the analogy to gravitational potential energy. Right? If everything is at the same height, everything has the same gravitational potential energy. Any object that you would put at that height would have that energy, so you could say the gravitational potential at that height is a certain value, and everything else has that same potential. Nothing's going to roll downhill in that case, right? Does that make sense? So think of charges as they move along electric fields or against them as rolling downhill or rolling uphill. You can make that direct analogy. We'll expand on that a little later. So, potential difference is what's important. Potential difference between, say, 2 points in space in which there's an electric field. And let me show you something. I don't know how well this is going to happen on the video. We'll see. I don't know if it's psychological, but I'm really hungry right now. Like, you guys are in here, and I haven't eaten yet, and it doesn't feel right, and my stomach, oh my gosh, I need to eat. I'm sure everyone at home wants to see that. Hi, Julie. Hi, Alex. Hi. Who else is at home? That's right, Jacob's back today. All right. So this is a little tube that has neon gas in it. You guys know what color neon is?
It's not a color.
It is a color. This is neon gas, periodic table, the noble gas, neon. You'll see what the color of neon actually is. So the other neon colors are just produced in a similar way, and so they call it all neon. But this is actual neon gas from the periodic table. So I'm going to run, if you run I forgot this part. Oh, jeez. And the video's not even looking at it. Oh, gosh. Jillian, you're slacking. This is it. Grant, do I need you to put your fingers in both of these while I plug it in?
I mean, if it helps, it'll just cost one free 100. That's great.
All right, I need my video editor to edit this part of the video out, please. If they can't get to that, I'm sorry for the people at home, but you are going to have to sit through this. And my 3 million YouTube subscribers, too.
You should make a YouTube channel like Flipping Flip. It's just you like messing.
That really hurt my feelings on the inside. I'm laughing to try to mask that.
Alex 2 times it right now. It's nothing important.
All right, so I have a tube with neon gas in it. There's no wires going through it or anything. When you run electricity through it, you guys were supposed to have learned, if you're in AP Chem, you should know this, that when an electron absorbs energy, it can be excited to a higher energy level where it will be unstable and it'll jump back down. And when it jumps back down, the energy that it had absorbed will now be emitted in the form of a photon. And that photon will carry the same energy that the electron lost as it jumped down energy level, conservation of energy. You guys learned about this, hopefully? Okay. So that's what happens here. I run electricity through it, and that happens. That's the color of neon. It's like an orange. And at some point, I'll let you look through a spectroscoping because you can actually take the wavelengths and split them into the constituent colors. And that's what led them to come up with the ideas of energy levels in the first place, because they couldn't explain why you only had certain bands of color whenever you look at the actual spectrum of a gas as it's emitting light. So that's it. What we need, though, for that to happen is obviously electricity to flow through this guy, through the tube. Electricity has to flow from one end to another. That's just what happens, right? So the thing is, if I take two batteries, say two D-cell batteries, and connect the positive terminal of one to this side and the positive terminal of another one to this side, what happens? Nothing, right? Nothing's going to happen because both ends are going to be at the same electric potential, right? If it's a D-cell battery, it's 1.5 volts. So each side will be at 1.5 volts, nothing will flow. You need a potential difference. That's not it, though, because if I charge my Van de Graaff here, oh my gosh, the things I go through for absent students.
Wait,
Not trying to make you feel guilty or anything, but
if you had a bigger battery on one side and a smaller battery on the other, then it would.
yeah. Because there would be an electric potential difference or a voltage difference.
And that would make the light.
Yeah, it just wouldn't light as much yet. Now, the batteries aren't going to be enough voltage to power this to make this happen, but if they were, then yeah, that would be true. So if I turn the Van de Graaff on, I know I'm generating an electric field. Right? It's a good thing we have a longer day today so I can make up for all this lost time here while I'm messing up. Am I getting an electric field? Yep. All right, so there's an electric field here, which means there's probably a potential difference because the farther away you get from the Van de Graaff generator, the smaller the electric field gets, and you would expect the electric potential to be reduced as the electric field goes down. Grant, what are you looking at?
The schedule. Just check.
Room 101. Okay. So you expect it to be different. You expect to have a potential difference, but I see nothing happening. Why is nothing happening there? There's no path for the electricity to actually flow, right? If I gave it a path, I could make electricity flow. But there's no path. And that's the thing. The potential in space, there's a potential difference in the space. But if there's nothing for that potential difference to actually push, meaning electrons to push, then it's not gonna do anything. It's just gonna have that field and have that scalar field, the potential field around it, but it's not gonna actually do anything. But I can have it do something by bringing this guy in. Zoom out just a little bit. There. No. All right. So I'm going to bring it in like this. And so the closer part will have a higher electric potential than the farther away part. So there will be a potential difference. I have provided a path for the electricity to flow inside of this tube. Good day for this. Now watch what happens when I hold it like this. It's nothing, right? I turn it like this, and I start getting it. Turn it like that. Nothing. It's really packing a punch today. So when I held it like this, why doesn't the charge flow? And yes, it did a little bit, but it's because I couldn't hold it perfectly there.
There's no path.
Both ends have the same.
No, there's a path
But
here.
it does have the same.
Both ends are going to have the same potential difference because they're equidistant from the source of the field. But when I'm like that, now they're not equidistant. Now there's a potential difference and a conducting path. That's what you need. You want electricity to flow? Those are two things. You need a potential difference and you need a conducting path. Yes, sir.
So if the tube was longer, would the light be stronger?
That's a good question.
It'll be more of a difference.
It's a good question. Off the top of my head, I don't know the answer to that. I'm going the wrong way there. I bet when we get to the part of this unit on potential on the actual energy and we can actually calculate it, we can answer that question. So I'm going to lie and pretend that I do know it, but I'm just going to say we're going to answer that question in the future. Or that question, the answer to that is beyond the scope of this class. So. Which is college professor speak, either for I don't know or that's too complicated and I really don't feel like explaining it to you. Could be one of those two. All right, so it's the potential difference that is important. So let's do a little bit of vector calculus. So we're going to do some math here in the language of vector calculus. What time does this class end, by the way, since you were looking on your phone in class? 20? Okay, that's enough time. We know vector calculus, right? So delta V, I want to know the potential difference from A to B. Okay? So and now I could do the potential difference from B to A or from A to B. What do you think switches when I go in one direction and then the other?
Just signs.
The sign, yeah. Final minus initial. As I move along the electric field lines, do you think I'm moving down in potential energy? A positive charge. If I release a positive charge at A and it moves to B, is it speeding up?
No.
If I put a positive charge here, say at A, positive charges, is it going to feel a force? It's the whole idea of fields.
Yes,
It will feel a force based on that electric field, and if it's positive, it would be that way, right? And so what's going to happen is the electron, or is the positive charge, is it going to pick up speed as it?
Yeah.
Yeah, it's going to accelerate, obviously. So it must be increasing its kinetic energy. The electric force is a conservative force. So the mechanical energy is conserved as charges move through electric fields. So we get that increased kinetic energy at the expense of potential energy. The energy stored in this charge that I stored whenever I did the work to put it there, right? So what I'm saying is that final energy minus initial energy will be negative here, right? Because I'll have less potential energy here than I will here because I have more kinetic energy there. If I go the other way, it's going to be the opposite. The final potential energy will be greater than the initial. So that's instead of letting this guy go from here, that's instead shooting that guy with initial velocity this way so that he ends up stopping him, right? Same interchange of energy, just in the opposite direction. What I'm saying is that the negatives really trip people up, including myself when I learned this. The equation that we're going to see in the next 10 minutes here really messed with my brain. I wasn't as smart as you guys, though. I wasn't as with it, so I struggled probably a lot more. But just understand that the negative there, the negative in the resulting equation can be tricky, and it can be a little sticky point for some people. But just understand that just like, if I'm thinking in terms of potential energy, more potential energy here, less here, the potential energy difference as I go from A to B is negative. If the potential energy difference is negative, the potential difference will be negative. If the potential energy difference is positive, the potential will be positive. And it does depend on which way you go. Okay? Which way do you go? It depends on the situation that you're dealing with. All right? All right, so let's just do some math now. I'm gonna rewrite this. Well, I'm gonna actually do the delta V now. And I'm gonna do final at B. So the potential at B minus the potential at A. All right, well, the potential at B, I can use this equation to calculate. So the potential, electric potential at point B, will be the integral from point B to infinity of the electric field dotted with dr minus the electric field, or the electric potential at A, which is going to be plus, right? Did I do this? Hold on. Oh gosh, I probably messed up again. I'm an idiot. This is a negative when I go from R to yeah. I was testing you to see how much you remembered about yesterday. Jacob Casillas, you fail. Oh gosh. I'm thinking ahead. You guys weren't wondering why that negative was there? Because we saw that it was negative if we talk about the work the electric force does, which points that way, as its displacement is this way, right? That's when the work is negative. So we saw yesterday that it was just the integral of E dot dr as we went from some location R to infinity. And that was positive, correct? That's what's in your notes? Okay, next time tell me that, Jillian. Because now I look real dumb. So delta V then is, I'm still going to do that. This is still right. This is how I knew something was fishy, because this wasn't turning out right. All right, so delta V then is going to be the potential at B, which is the integral from B to infinity, using this equation, of the electric field dotted with dr. And if it's an electric field is drawn like this, it's usually like a uniform electric field, so it's going to be pretty constant in that space. All right, and then minus the integral from A to infinity of E dot dr. And then I'm just gonna do some finagling here to make this end up looking like what's on your formula sheet. Delta V, and remember delta V, we're talking as we go from A to B. How do I know that? Because this is my final, this is my initial, right? Final initial. So delta V then, I'm going to, I want to combine those into one integral. Is there a way of doing that?
Yes.
There is? Can you tell me about it? So remember calculus?
Yes, sir.
So if I have a function, f of x, and I want to find, and I have an equation, I want to go A to B to C. This is just kind of a demonstration. In this case, the integral to get this area and this area, the integral from A to C of f of x dx
Oh, yeah.
is equal to what?
A to B plus B to C.
So these two limits match, and then it just goes, well, that limit to that limit, right? Graphically, you can easily see why that's true. It's kind of weird when we're dealing with infinities, but we can do the same thing.
You just switch that to positive, right?
Well, we could do that, but again, I'm doing it in the way that is usually done, and it's kind of confusing. But yeah, instead of doing what a normal person would do, we're going to flip this one. And we're going to have the negative integral from b to infinity. You'll see why whenever we get to the end, and you'll see what's on the physics equation sheet, minus the integral from a to infinity. Oh, no, I did that wrong. Minus infinity to b, yeah, e dr I'm doing this. And now I can just do the same thing here, right?
Would it not just be from B to A?
Oh, that's okay. Wait, yeah. I want to switch these, right? Wait. That's what I want to do. Yeah. Okay. So it's gonna seem weird, but I'm gonna write again. You'll see why in a second. I'm sorry. I'm not doing well today. Minus, so from a to infinity, and then the integral from infinity to b of e dot dr. And there is a reason for this. I know it's not what most people would do, but this is the way that the final equation gets derived. So with that, then I can write, this is delta V, which again is VB minus VA. I'm showing you why it's confusing, by the way. I'm showing you why this gets confusing, and then we'll spend the beginning of next week on like making it so it's not as confusing as it seems now. So I'm going to have that written as an integral. I'm going B minus A, but I'm going to integrate from A to B. So it's weird. So the delta V then is going to be, I'm going to factor a negative out, and then I'll have the integral from A to B of E dot dr. Yes, if we had done what Jacob had suggested and just do it the other way, then it would be the integral from B to A, and there would be no negative there.
Oh.
Right? So that, but, and it's not just the College Board on this one. Like all physics textbooks are going to have it written like this. On the formula sheet, it says that delta V is equal to the negative integral of E dot dr. That's all it has on the formula sheet for potential difference. Okay. And the limits behave weirdly. And the key to understanding whether your answer should be positive or negative, draw a little diagram with the direction of the field. Look at the locations. Okay. The location in the direction of the electric field, we get reduced potential energy as we travel. Why? Because we pick up kinetic energy, and the force is conservative. So I know that the potential energy here has to be less than here. So if we want VB minus VA, it better be negative. If it's not negative, then you did something wrong. You probably used the wrong sign, right? If you want the potential energy A minus B, well, final minus initial, that is going to be positive because this point would have more potential energy than that point. And yeah, potential and potential energy aren't the same thing, but if change in potential energy is positive, change in potential is positive also. If delta U, yeah, me too. If delta UE is negative, then delta V is also negative. All right. So we'll have a test over this on Monday. Be sure you study for Maxwell's equations. Last test of the year. Then I'm going on a long vacation. Please subscribe.